Hello and welcome to Orange Tutorials. My name is Ida and I'll be your guide in the world of data science. Let's dig in. You have probably already downloaded and installed Orange. If not, you will find the detailed installation guide in the link below. When you open Orange, the first thing you will see is a welcome screen. From here, you can start a new data analysis workflow, open a recent one, or explore tutorials. Okay, let's exit the welcome screen. Orange starts with a blank canvas. This is where all the magic will take place. But every magic needs some secret ingredients. Our ingredients are called widgets. Widgets are computational units of Orange. They read the data, process it, visualize it, do clustering, build predictive models, and otherwise help you to explore the data. You will find them on the left-hand side of the screen. Most data analysis workflows begin with the File widget, with which we load our data. Click on the File widget and it will appear in the canvas. Open it with a double click. Go to Browse Documentation Sets and load one of the existing data files that come with Orange. You can naturally load your own data, but for the sake of simplicity, let's go with the famous iris dataset. Now we would like to see what we've just loaded. Click on the data table and the widget will appear in Canvas. Widgets communicate with one another. They have an input channel, an output channel, or both. To feed the data from the File widget to the data table, drag a line from the right output side of the File widget to the left input side of the data table widget. Now open the data table. Wow, that's a lot of numbers in columns and rows. Let's instead plot the data. We will use scatterplot and connect it with the File widget. Much better. And with this, you've just set up your first workflow. Congratulations! Creating a data analysis workflow in Orange is simple. We start with opening the data in the File widget. Some preloaded data sets are available, so let's select Iris and explore it. Let's check out the data in a data table. I will select the data table widget and connect the File widget to it. Here we have 150 iris flowers from the famous fishes dataset. Flowers are described by 4 features: the length and width of sepals and the length and width of petals. Each flower is labeled with one of the 3 classes, a species of iris: Iris setosa, Iris versicolor, and Iris virginica. Now let's visualize the data. I'll connect Distributions widget to the File widget. In this way, the File widget sends any data it loads to the Distributions widget. In Distributions, we can walk through all the features in the data. Petal length and petal width seem to nicely separate different species of iris. We can additionally inspect the data in the scatterplot. The plot that we see is a bit messy. Iris versicolor in red and virginica in green are not well separated. I wonder if there's any pair of features that would nicely separate the 3 classes. I can click Rank Projections to score all feature pairs. A higher score indicates a better separation of different species of iris. The best scored scatterplot, with petal length and petal width, really nicely separates data instances of different class. But there's some overlap of Iris versicolor and Iris virginica. I'll select data instances in the overlapping region. Scatterplot widget automatically sends the data to its output. Now I connect another data table to the scatterplot to inspect selected data instances. No surprises here. They are all either Iris versicolor or Iris virginica and seem to have similar values for all 4 features. We can expand the workflow with other widgets or save it for frequent use. But for now, that's it. We've learned that Orange widgets communicate with one another and the changes in one widget are immediately propagated through the workflow. Today I'll show you some great functionalities of Orange data mining widgets and communication channels. In Orange, there are several ways to add widgets to the workflow. A. Click on the widget in the widget pane and the widget will appear in the canvas. B. Click and drag the widget onto the canvas to place it exactly where you want it to. C. Right-click on the canvas and the widget menu will appear. Select the widget from there, or even better, start typing its name in the filter. Select the widget and press Enter. D. Drag a communication channel from the output of the file widget, and orange will suggest the widgets you can connect your original widget to. Remember, orange will not allow you to connect incompatible widgets. To get more space for the workflow, go to View and deselect Expand ToolDock. I, for instance, have the widget toolbox minimized at all times and use the right-click to add new widgets. You can also tell Orange what kind of data you would like to send from one widget to another. Here is a simple example. We will use iris data from our previous video. I will first connect scatterplot and data table to the file widget. Let's see if the data was received by the scatterplot. Yes, it's here. Let us also connect the data table to the scatterplot. The idea is that I will select some data instances in the data table, and these instances will be highlighted in the scatterplot. I will open data table and select some instances. The widget is sending my selection straight to the scatterplot. See how scatterplot marks selected instances? I have indeed just created a visual data browser. Now double-click on the link between data table and scatterplot. Orange correctly guessed that the data from the data table will be used as a data subset in the scatterplot. We can change that and remove this connection by clicking on it. Now we can drag a new line from other data to data subset, and the plot will change. All data instances other than those selected in the data table will be highlighted. This is how you can define what is communicated between widgets. You don't need to do this often, as Orange matches the inputs and outputs automatically, or infers the right connections from the order in which you've added widgets to the workflow. A right-click on the communication channel allows you to remove the connection. Today, I've showed you the many ways to add widgets to the workflow, how to adjust the input and output of a widget, and of course, how to turn a few widgets into a cool data browser. Preparing your data so the programs can read it is probably the most important task in data mining. Today I'll show you how to load your data in Orange. Orange can read several data formats, such as Excel, tab, and comma-separated files. The data is normally a table where data instances are in rows and data attributes are in columns. But why just do the talking and no walking? Let's make our own data. I'll use Google Sheets to create a simple data set. Say we have a group of people and we would like to know whether we can predict the gender based on their physical characteristics. Okay, our people will have a name, so we know who's who. Then we also know their gender, height and weight, and we know how they look like. So let's put down also their eye and hair color. I have this data set for my friends, Jill, Jack, Mark, Anne, and so on. Their names are all strings, that is text. Gender won't be a string, but a categorical value, because our people will belong to one of the two groups, male or female. My friends naturally have different heights and weights, which are numerical values. Some of my friends are tall, others short, some slim, and others a bit chubby. The color of their eyes and hair are again two categorical values, since the eyes can be either blue, brown, or green, and the hair black, brown, blonde, or red. Now we have our data. Still, other than providing the data, I have not explicitly specified attribute types, so let's hope Orange will guess them correctly. Now we load our data in Orange. Let's copy a shareable link and paste it into a file widget. Let us first view the data in a data table. Orange correctly assumed the first column with names contains our meta attributes, but it incorrectly made the hair color our class variable. Maybe I should have gender as the last column in the table. But let us fix this in Orange. we can rearrange the data with Select Columns widget. We'll put hair color attribute into features and gender in target variable box. One quick check in a data table, and we're good. You can also save the data to your computer with Save widget. It's best to save the data in Orange's native tab format, since it automatically appends header annotations for attributes. You might want to define your data locally. I will use the same data as before, only this time I copied them to Excel. I will add 2 extra rows under attribute names. Set variable type in the first one and variable kind in the second. For the attribute type, I will use C for continuous, that is numerical attributes, D for discrete or categorical attributes, and S for string values. For the attribute kind, I will write class under gender and meta under the attributes that provide some extra information. Now our data is all set for the analysis. Today we've learned how to prepare our data, manually annotate it, and subsequently adjust which feature is considered a class attribute. By now we know that we can visualize our data and browse through data subsets. But what else can we do with our data instances? Perhaps put them in logical groups. We will use the good old iris dataset as in our previous videos. We've already observed that flowers are different, but how do we know whether they're just one single group of flowers, like one single species, or they belong to different groups of irises? I will show you how to discover groups, and possibly subgroups and sub-subgroups, using a method called hierarchical clustering. So, how does this clustering work? Naturally, we would like to group the flowers together so that those with similar leaf measurements would belong to the same group. For 2 flowers, we can check each measurement and compute the difference between the measurements. Square it to make sure it's positive, and then sum the square differences across all 4 measurements. At the end, we can compute the root of the sum to match the original measurement units. I've just reinvented the Euclidean distance. Still, we can see from here that the smaller the distance is, the larger the similarity. Flower distances can now be used to construct hierarchical clustering. Connect the hierarchical clustering widget with the distances widget. Hierarchical clustering displays a dendrogram, which is a tree that reveals the structure of the discovered clusters and the distance between these clusters. Let's make this dendrogram more telling and annotate the branches with the species of iris. It looks like clustering indeed made sense of the data, as flowers of the same species are clustered together. However, there's an area with some mix-up. Let's mark it. Selected flowers, I mean data instances, will be on the output of hierarchical clustering widget. To check these instances, we will send them to the data table. And voila, here they are. Looking at this data table, I'm not much smarter. Wouldn't it be cool to see these selected flowers in some visualization and say in the context of every other flower in our data set? We've done this before and we'll do it again. We will use scatterplot widget to visualize all 150 flowers. No, not this visualization. I want the interesting one. Here it is. Now connect hierarchical clustering to the scatterplot. The mix-up is, naturally, in the bordering region between Iris virginica and Iris versicolor. We can now browse through clusters in hierarchical clustering and observe their mapping in the scatterplot, just like we did in the previous video. It helps if we have both windows open at the same time to observe the results. This is how Orange became a tool for cluster exploration. There is so much more you can do with clustering in combination with other orange widgets. But for today, this is it. We've learned that hierarchical clustering requires information on distances in the input, that it displays a dendrogram in the visualization, and that we can select data instances in the clusters of the dendrogram to output them to other orange widgets. One of the great things about being a data scientist is being able to predict the future. Of course, I'm not talking about an old lady in a crystal ball, but rather predicting from solid data with some degree of certainty. Today, I'll show you how to use Predictions widget to predict class labels for instances in our dataset. This time, I'll be using data on fruits and vegetables. Because I will use this data to train my classifier, I will refer to it as a training dataset. We have 9 features in the training set, including the calorie count, proteins, fiber, vitamin, and mineral content. Based on these features, we would like to predict whether a plant is a fruit or a vegetable. Of course, we're interested in which features are the most important for our classification. What tells us best if something is a fruit or a vegetable? We'll check this with Classification Tree Viewer. Here, we can nicely visualize which features best split the data to pure subsets, where one of the classes prevails. In our case, the most important feature is the calorie count, and then the content of vitamin A and proteins. So most likely, these will be the deciding factors in our predictions. Okay, now it's time to make some predictions. Say I have my own fruit plants, for which I would like to know whether they're a fruit or a vegetable. I know their potassium, vitamin, and calorie values, so let's write this down in Google Sheets. The one thing I need to be careful of is to use the exact same names for the features in my test dataset, so that Orange can match them correctly. Now let's load the data in Orange and read it in the Data Table widget. Okay, all of our data is here. Connect the File widget with Predictions. Do we see anything yet? Of course not. We need to give the widget some classification model first. Actually, I've already built the model from my training set with the Classification Tree widget. Now all I need to do is connect the classification tree to Predictions. I can now view the predictions directly in the widget. Seems like 2 of my plants are a fruit and 1 is a vegetable. Of course, I can use other classifiers as well. A fast and simple one is logistic regression. I wonder if its predictions will be different. Let's check. Again, I will connect logistic regression widget to the File widget and then pass the predictor to Predictions. Seems like logistic regression agrees with predictions from classification tree. As a matter of fact, I have used the actual data for a kiwi, asparagus, and a raspberry, that is 2 fruits and a vegetable. Predictions were indeed correct. Today we've learned how to classify data with classification tree, how to build prediction models, and finally how to use them on a new dataset. While we have made the predictions, we have not really evaluated how good these prediction models were. In the upcoming video, we'll talk about model evaluation and scoring. In the previous tutorial, we've made some predictions on fruits and vegetables. But you've been probably wondering, how do we know which classification model works best? Today I'll show you how to assess the quality of various prediction methods. This time, we're going back to our good old iris dataset. First, we will train a model with one of the simplest classification techniques, a logistic regression. To avoid overfitting, we are first building the model on the training data and then testing it on a separate test data. We want to repeat this procedure multiple times and then report on average accuracy. This is what cross-validation does, and it can be found in the Test and Score widget. In our case, cross-validation splits the data into 10 subsets, uses 9 for training the model and the remaining subset for testing it. It repeats this procedure 9 more times, each time using a different subset for testing. Cross-validation results are reported on our right. What do these numbers mean? The simplest one to understand is classification accuracy in the second column. It reports on the proportion of correctly classified data instances. Looks like classification accuracy was 96%. So what are the 4% of the data that were misclassified? We can check this with confusion matrix. Looks like our model had no problems with classifying irisitosus. Still, it got a bit confused with versicolous and virginicus. We can easily observe misclassifications by selecting misclassified instances and sending them to the data table. Just by looking at this table, it is still hard to interpret the results and say much about misclassifications. Instead,
enjoy the
let's
rest of your
visualize them
workday.
in scatterplot. Most misclassifications are at the border area between the two classes, the red for Iris versicolor and the green for Iris virginica. We expected something like this, right? Logistic regression is, of course, not the only classification method we can apply on Iris. We could use, say, random forest. This is a more complex classification technique, but often has better accuracy. However, not in this case, where the accuracy of logistic regression is already quite high. Besides accuracy, Test and Score widget reports on 4 other scores. We really like the area under receiver operating characteristics, or AUC in short. But that will be the topic of some other tutorial. We can also check where misclassifications lie for random forest, but I'll leave this to you. Today we've learned how to use cross-validation in Orange and how to compare several classifiers on a single dataset. I've also showed you how to select misclassifications and visualize them. By now you know Orange quite well. But how about if you want to do some specialized research in, say, bioinformatics or text mining? Add-ons are coming to the rescue. You can find add-ons under Options, Add-ons. This will display a package list from where you can install the add-ons you want. Say you want to go with bioinformatics. Select the package you wish to install and press OK. Now restart Orange and you will see an additional widget set on the left. OK, let's explore what's in the add-on. There are some visualization widgets, some specialized data analysis techniques, and a few widgets that offer access to external databases. One such widget is GeoDatasets, that offers access to a large repository of gene expression profiles. There are a few thousands of datasets you can load from the widget. Say I'm interested in researches on smoking. We first filter the data on this keyword. Now let's select a small dataset. This one looks nice. First we want to see what kind of data we got. These are gene expression data for 5 smokers and 5 non-smokers. We have gene expressions in columns and samples in rows. Now we want to visualize this data to quickly check if there's any difference between smokers and non-smokers based on their gene expression profiles. There are so many features to choose from, so how do we make sense of it? Multidimensional scaling will help. This technique projects multidimensional data to a 2D space. We see there are 2 nice groups, blue for non-smokers and red for smokers. And there is one sample from a smoker, which is an outlier. This could be very helpful. Even if we're not molecular biologists, we can see that smoking leaves a trace on a cellular level. But enough biology for now. Multidimensional scaling and other embedding techniques are a great way to understand the underlying patterns in any kind of data. We will talk more about 2D embedding in the upcoming tutorial. As for today, we have learned how to install add-ons in Orange and how to use new widgets in combination with the existing ones. Data can be more or less complex. Imagine a data set with many features, say 100. How do you know which features matter the most? And how could you possibly project the data onto a 2D plane? One of the popular techniques to answer this question is principal component analysis, or PCA in short. PCA transforms the data into a new attribute space, where features are uncorrelated and ranked by the degree of explained variance. Let me show you this by painting some data. Although this data is in 2D, we could identify the position of each point just by knowing its coordinate in a new tilted axis. This would also be our principal component. Its direction is defined by the vector PC1. If our data lie in a many-dimensional space, maybe only a couple of principal components are enough to explain it. Let's see this in action. This time I'll be using wine dataset with 13 features. A 13-dimensional space is difficult to grasp, so we'll be using PCA to transform the data into fewer dimensions. How do you know how many principal components to go with? The best choice is to select the first few principal components that explain, say, 80% of variability. Orange shows the proportion of explained variance in a scree diagram. 5 principal components in my dataset already explain slightly more than 80% of variability. I can check the transformed dataset in the data table. Now let's see how our transformed data looks like in scatterplot. I will plot the data using just the first 2 components. The 3 different vines are really nicely separated. Turns out that chemical components called flavonoids are those that define the first component the most, followed by phenols. Today we've learned how to transform our data into a set of linearly uncorrelated features with principal component analysis. Next time, we'll show you another way to rank features with rank widget. In our previous video on principal component analysis, we used wine dataset. These data are the result of a chemical analysis of wines grown in the same region in Italy, but derived from 3 different cultivars, or vines. The data include 13 features reporting on quantities of chemical components. How do I know which chemical components are the most significant for differentiating between these vines? With rank, of course. This widget scores features with several scoring methods, based on the relation with class. Connect file widget with rank. Rank displays 2 scoring methods as a default, but we can display more if we want. Say I want to see the scores for gain ratio, Gini, and relief F. Now I want to select the features with the highest relief F score. By default, the top 5 features are selected and are already on the output. Now I want to see how well are these features related to class. Let's use some visualizations for that. Connect boxplot to rank and inspect the first feature. Use group by wine to see the results for each class separately. Boxplot reports on mean, median, variance, and quartiles of each feature. Mean is displayed as a vertical blue line. Median as yellow. The blue highlight denotes variance, while the dotted lines display the first and the fourth quartile. The wines seem to have very distinct distributions of flavonoid concentration. Seems like this feature separates the class very well. But there must be an even better way of inspecting our features. How about distributions? Let's see. Distributions widget displays a value density plot for a given feature. We can display value distributions for each class separately. For flavonoids, these three distributions seem to be well separated. Flavonoids are likely one of our most important features in the dataset, as the separation is less pronounced with other features. Rank widget can score and rank features both for classification and regression. Say we want to analyze a bit dated housing dataset, where we would like to check which feature best correlates with the house price in Boston suburbs. Seems it's the economic status of inhabitants and the average number of rooms. Sort of obvious, but it's still great to see this directly from the data. Today we've learned how to determine which features are the most interesting in our dataset, and how to use feature scores for plotting interesting visualizations. Almost every data mining problem describes the data with features, thus making feature scoring one of the best loved techniques in the field. In data analytics, one often needs to find interesting groups of data instances. May that be segmentation of customers based on their shopping habits, finding similar documents, or grouping tweets based on their content. Especially when the data abounds, we can find clusters using a method called k-means. First, let us paint some data to see if clustering really works. We will make 1, 2, 3 groups of data points. Now let's connect paint data with k-means. This widget finds clusters so the data points in the same cluster are close to each other. That is, the distance between them is small. Here, we told k-means to find 3 clusters. Now we can observe the clustering in scatterplot. Wow, this worked fine. And the k-means really discovered clusters where we had expected them. We can interactively change the number of clusters and observe these changes in a plot. We can ask for 2 clusters, 4, 5, and so on. For our data, the choice of 3 clusters works best. K-means requires us to specify the number of clusters. But in Orange, we can also ask it to find the right number of clusters. We can tell it to vary the number of clusters, score each clustering, and return the best score. But how do we score the clusters? With Silhouette. Silhouette scoring reports how well each data point, on average, fits into its designated cluster. The higher the score, the fewer data points we have where clustering membership is not clear. Let's instruct k-means to use the Silhouette score and guess the best number of clusters. It's 3, just as we expected. Let us add a few more clusters to our data. 4, 5, 6. Now this looks simply wonderful. Every time the k-means with Silhouette scoring correctly guess the number of clusters. Is it even possible for k-means to make a mistake? Let's see. We will draw 3 clusters in the shape of a smiley face. Let's see what Silhouette suggests. 4 clusters? That can be right. Obviously, there should be 3. This is one of the drawbacks of k-means. It works well on compact, spherical-shaped clusters, and fails on shapes of a different kind. Now let's use k-means on a real dataset. Boston housing prices, for example. We will ask for 2 clusters and then observe the differences between clusters in the box plot. Looks like there are major differences between the clusters in this data with respect to the crime rate, pollution, and age of the houses. We can even check if clusters make sense in the MDS data projection. Well, they do. This dataset indeed has two distinct clusters. Today we've learned what k-means does and how to use it on a real dataset. In the next two videos, we will explain how k-means and silhouette scoring work and how silhouette can find inliers and outliers. In the previous video, we talked about k-means clustering and how we can find interesting groups in our data. But how does k-means actually work? That's easy to find out. We can use interactive k-means from our educational add-on. This add-on is designed for teaching machine learning, and it includes some wonderful instructive widgets. To install it, go to Options, choose Add-ons, and select Educational. You will need to restart Orange to make the widgets from this add-on active. We will first plot a dataset with three groups of data instances to see if we can retrieve them with k-means. Now connect pane data to interactive k-means. Besides the data, the widget also plots the centroids marked with squares, each one in its own color. Centroids are the assumed centers of clusters. Interactive k-means places them randomly. Notice that each data point is associated with the closest centroid. In this way, the centroids define the clusters. But while we have free clusters, they're not the ones we would wish for. First, it would be better to move the centroids to the center of data points. We do this by pressing Recompute Centroids button. The centroids moved. Look at the red centroid. Some green and blue points are closer to it than to the other two centroids. We need to reassign centroid membership so that the data instances are labeled with the closest centroid. We do this by pressing Reassign Membership. We can again move the centroid to the center of its data instances using Recompute Centroids, and again reassign the membership. We repeat these two steps until convergence. That is, until the position of the centroids does not change. For our data, the convergence took only a few steps, and the algorithm found the appropriate clusters. Now let us try to place centroids so the algorithm would fail. Here, I will put the red centroid in between two groups of data points, and the green and the blue centroid so that they share the remaining group. Now press Recompute Centroids and reassign membership a couple of times. The algorithm converged, but the clustering it found is not the one we had wished for. Today we've learned how k-means finds clusters with the help of an interactive visualization. We also learned that the initial placement of centroids is important. This is why k-means normally uses some heuristic for smart placement and reruns the algorithm a couple of times to report only on the best clustering. In the previous videos, we talked about k-means and how to find a good number of clusters in our data. We mentioned silhouette, which is a score of cluster quality and helps us find the k to our means. Understanding how silhouette score works is quite simple. Here we have three clusters: green, blue, and orange. Now we would like to know how well this data point belongs to the blue cluster. First, we will measure the average distance between our data point and the points in its own blue cluster. Let's call this distance A. Second, we will measure the average distance between our data point and the points in the closest green cluster. Let's call this distance B. If our data point is well grounded in its cluster, B needs to be large and A small, so that the difference between them, B minus A, is as large as possible. To normalize this score, we have to divide it by the maximum of A and B. The silhouette score for our data point will be quite high, since it lies close to the center of its cluster. A silhouette score for a point that lies in between the two clusters will be close to 0. Let me now paint some data. I'll pass it through k-means clustering and visualize the clusters in the scatter plot. I will use Silhouette widget to find points that are close to the center of the red cluster. To observe where the selected data instances lie, I will connect Silhouette to the scatter plot. Let me select a few top scored data instances in the red cluster. Wow! They are indeed in the center of the cluster. And those with the lowest scores, they are the borderline data points. I can use silhouette plots on any data that include discrete class or attributes, say on an iris dataset. The biggest outliers are in the overlapping region between iris versicolor and iris virginica. And the inliers, most of them lie in the well-separated iris setosa class. Today we've learned about the mechanics of silhouette score. In the previous videos, we had used it to score the clusters. But what a great tool it makes for finding the inliers and the outliers. Data can come in all shapes and sizes. It can be a simple spreadsheet or a complex text, audio, video, or even an image. Today I will show you how Orange transforms images into numbers and in this way enables machine learning. First, we will have to install Image Analytics add-on. Go to Options, Add-ons, and install Image Analytics. Restart Orange for the add-on to appear. Now let's start with an example. I have collected 19 images of domestic animals and placed them all in the same folder. I can load them in Orange with Import Images. Open the widget and select the folder. Now connect Image Viewer to import images. Looks like we have all the animals here. Import Images actually constructs and outputs a data table. But how does this data table look like? Let's check this in a data table widget. All I have is a bunch of meta information. Image name, image file path, size of the file, image width and height in pixels. Nothing that would help me with machine learning. We need image descriptors, that is, numbers which describe the content of these images. We will transform raw images into their vector representation using a deep neural network which was trained on millions of real-life images. Retrieved vectors are also called image embeddings. We embed our images into a multidimensional feature space. Connect import images to image embeddings. The widget sends images to the server and computes embeddings remotely. Let's see what we got back. Now, we don't only have meta information, but also 2048 additional features to profile the images. Great! With embeddings, we can compare the images and compute their similarity. Let us pass the data to distances and select cosine distance, as it usually works best for images. Then, we can pass the distance matrix to hierarchical clustering and observe the dendrogram. Seems like embeddings indeed make sense. All the chickens are grouped together, and all the cows too. I can even check each cluster in an image viewer. Simply wonderful. But I know what you're going to say. You think I'm trying to trick you, that I intentionally selected similar photos so they would get clustered together. Let's double check our procedure with the most famous cow in Europe, the Milka cow. This image is quite different from the others. It is a frontal photograph with digitally enhanced colors. I have retrieved the image from the internet and added it to my domestic animals folder. If I press Reload in Import Images, the new image gets loaded and the whole workflow is instantly updated. Let us again open Hierarchical Clustering and Image Viewer. Seems like Milka is correctly clustered with its kind. Today we've learned how to work with images in Orange, profile them using deep model embeddings, and perform clustering. In the next video, we will go a step further. We will be building predictive models for image classification. In the previous video, we talked about how to transform raw images into vectors and use these embeddings for clustering. But we can do much more with images. We could, for example, use them for classification. Say I am an owner of an online flower shop. I have many images of flowers, from roses and daisies to tulips and orchids. Can orange tell a tulip from an orchid? Let's check. I have created a folder Flowers with 9 subfolders containing images of different flowers. We already talked about spreadsheets and images. How about text? Could we extract any meaningful information from a set of documents? Of course we can. First, we need to install Text Add-on. Go to Options, Add-ons, and select Text. Restart Orange for the add-on to appear. Now, let us load the data. Place Corpus widget on the canvas and open it. Go to Browse Documentation Corpora and load Green Tails selected. We have 44 green tails on the output of the widget. What are these texts about? Connect Corpus Viewer to Corpus. Corpus Viewer displays text and enables us to browse it. For example, we can output only those documents that contain the word king. Another widget for visualizing the text is Word Cloud. This widget displays word frequencies in a cloud. The more frequently the word appears in the text, the larger the word will be. But our word cloud shows silly things, such as punctuation and uninformative words. We will use preprocessed text to get rid of these. This widget will transform all text to lowercase. Next, it will convert text into individual words and omit the punctuation. Individual words are called tokens. Finally, it will filter out stop words. The effects of preprocessing can be visually explored in the word cloud. After preprocessing, this visualization looks much better. We retained only meaningful words, and now we can better understand what our corpus is about. Grimm's tales talk about kings, fathers, and wives. But some words are still a bit annoying, such as could, would, and said. We can filter these out as well. Let us write our own custom stop word list. Open a plain text editor and type each word you want to filter on its own line. Then save the file and load it next to the preset stop word list. The changes are now propagated through the workflow, and the words we defined in our stop word list no longer appear in the word cloud. Preprocessing is the first and a very important step in text mining. We defined our tokens and filtered out the bits we didn't need. Now our text is ready for the next step. In the following video, we will use preprocessed data to find interesting groups in Grimm's tales. In the previous video on text mining, we talked about text preprocessing. Now our data should be ready for machine learning, right? Well, not quite. After preprocessing, Orange still sees only lines and lines of text. For machine learning, we need to transform text into numerical representation. And a simple way to do it is to count how many times each word appears in the text. This approach is called bag of words. Let us reuse the workflow from our previous lesson. Corpus reads the collection of text documents, and text preprocessing removes stop words and delimiters. Now we will extend the workflow with the bag of words widget. Bag of words outputs a data table where word counts are the new added features. You can always check the output of a bag of words in a data table. Great! Now we have our data matrix, and we can find interesting groups of documents. Connect distances to bag of words. Here, we will use cosine distance, as it normally works best for corpora. We feed computed distances to hierarchical clustering. To estimate the distances between clusters, we will select word linkage. Now drag a line at the top of the visualization left and right. What is the appropriate number of groups? 2 seems to make the most sense. The nodes in our dendrogram also have a label. In folkloristics, Grimm's tales are labeled with Arne-Thompson-Uther index, which defines the topic of the tale. If the tale talks about animals, it's an animal tale. If it's more about dragons and princesses, it's a tale of magic. Looks like the tale type corresponds quite well with our clusters. Except for one part, where animal tails and tails of magic are mixed. Can we figure out why they're mixed? Select the cluster and connect Corpus Viewer to hierarchical clustering. Seems like some tales of magic still mention animals. Perhaps clustering got it right after all. Clustering is a great way to uncover similar documents in unlabeled text. But here we actually have labels, the ATU topic. In the next video, we will talk about classification and try to predict the type of the tale on fresh data. We already know how to preprocess our corpus and how to find similar documents with hierarchical clustering. But Grimm's tales also have a label. The tales are either animal tales or tales of magic. Can we use this data to predict the type of a new, unclassified tale? We read Grimm Tales Selected and check the data in Corpus Viewer. Tale labels are provided in ATU topic field. We prepare the text with preprocessing and turn it into a bag of words, which represents each tale with a vector of word counts. Now for the classification. Connect logistic regression to bag of words. Logistic regression constructs a model to predict whether a tale is an animal tale or a tale of magic. We can even see how our model looks like. We will use nomogram, which visualizes the logistic regression classifier. Connect it to logistic regression. The widget displays top 10 words that are important for the classifier. At the top of the list are the words that most contribute to the prediction. Seems like the word fox can tell us a lot about the tale. If fox appears often in the text, it's an animal tale. If it doesn't, it's probably a tale of magic. Now we know how our classifier works, and it's time to see if it also performs well. Connect test and score to bag of words. We will use test and score to cross-validate the logistic regression model. Not bad. The area under RRC curve is over 0.9. When given two tales of a different class, logistic regression can correctly distinguish between them in over 90% of the cases. But we said we want to predict the tale type, right? And we don't want to predict something we already know. We will place a new corpus widget on the canvas. Let us load 3 new tales from Hans Christian Andersen. We will ask our logistic regression model to tell us what are the types of these new tales. Connect Corpus 1 to predictions. Now provide the Grimm-trained logistic regression model and observe the results in predictions. Our model says the ugly duckling is an animal tale and the little match seller a tale of magic. Seems quite right. Predicted class probabilities were high as well. The probability that the ugly duckling is an animal tale is 90%. Today we've learned how to inspect our logistic regression model with nomogram, how to reuse the familiar classification workflow on text, and how to predict the type of the tale on new corpus. Working with text in Orange is just as simple as working with spreadsheets. In the previous videos, we talked about text preprocessing, clustering, and classification. We worked with Grimm's tales, a dataset I have prepared in a spreadsheet. But working with spreadsheets and long text can be a pain. Is there any other way we can import texts into Orange? Of course there is. This time, I will work with Kennedy's speeches. I have 17 of them in a Kennedy folder, each in its own file. Files can be Word documents, PDFs, or plain text files. Here, for example, is a speech from Democratic National Convention. To load corpus into Orange, open Text add-on, place Import Documents widget on a canvas, and open it. Click on the folder icon and select the folder you wish to import. Let us observe our data in a corpus viewer. Here's the speech we've seen earlier. Now I can do some clustering. I'll use preprocessed text, bag of words, distances, and hierarchical clustering. I was fast. For details on text preprocessing and clustering, you can check our previous videos. Looks like I have two interesting clusters, one on nuclear arms and the other with Kennedy's presidential addresses. Clustering is fine, but what about classification? Can I tell Orange some documents belong to one group and others to the other? Let us put Kennedy's speeches into two folders, say pre-1962 and post-1962. Now, reload the folder. Orange recognized subfolders as class categories. If we observe the corpus in a data table, we can see that Orange put pre-1962 and post-1962 in the gray class column. You can check our previous videos on text classification to learn how to proceed. Import documents makes it so much easier to organize your files and your research. Today, we've learned how to import our own data for text analysis and how to define class values from scratch. We love our data, but most of the time our data is big with many variables, and making sense of it is a difficult task. Well, not so difficult in Orange. Let us load the iris data that we have used in some of our previous videos and connect it to scatterplot. Scatterplots are great. They can show us the relationship between two variables. But our data rarely has only two variables. Even iris data has 4. How could I see the relationship between more than two features? With Freewiz. Freewiz is a multivariable projection method for uncovering feature interactions in a data with class variable. If we pass iris data to Freewiz, the widget would initially place the variables on an invisible circle, making them equally important. Press Optimize, and Freewiz will rearrange the projection and find the one that best separates points of different classes. By doing this, optimization exposes the most relevant features of the data. Variables associated with longer axes are more important for a specific class value. And those variables that lie closer together are more correlated too. Iris setosa flowers, which are marked with blue circles, have high values of sepal width. And large petals are distinctive for Iris virginica. On the other hand, sepal length does not play any role. Let us see this on a different example. The zoo dataset contains 100 animals classified into 7 groups, including mammals, fish, bird, and so on. We will use Freewiz projection to investigate relationship between all 15 variables and see whether there's some structure in the data. In the File widget, simply change Iris to Zoo with Browse Documentation datasets. In Freewiz, we instantly see the unoptimized projection. Let's use Optimize again to reveal the relations between features and animal classes. We can even use Show Class Density to observe whether the data projection in Freewiz really managed to distinguish between different class values. It looks like it does. Having hair and giving milk is a distinguishing property of mammals, while being aquatic is a property of fish. On the other side of the projection are those animals that lay eggs and have feathers. This means mammals do not have any of those two properties, since they are placed opposite of the two features. Finally, at the center of the plot, we see features that are not very informative, such as animal domesticity. We can exclude these features from the graph by increasing the blackout radius. Visualizations make data interpretation so much easier. In this video, we learned how to uncover interesting relations between classes and features in a class label dataset, and how to interpret the Freewiz projection. Every machine learning needs numbers, be they in a spreadsheet form from the beginning, via feature construction, or in the case of text mining, with bag of words. Today, we're going to have a look at an alternative way of describing documents with vectors, by using document embedding. First, let us prepare the data. We will start with Corpus widget and the preloaded dataset of Grimm's Tales. A quick look at a Corpus viewer gives us an idea of what the data is about. These are the fairy tales of the Grimm brothers, such as Cinderella, Little Red Riding Hood, and Snow White. Now we wish to describe the content of the tales with numeric features. But first, we need to prepare the core units of our analysis. This will be a quick setup. For a detailed guide, see our text preprocessing tutorial, whose link is in the description below. The presets that we have are already quite good. Our text is transformed to lowercase and split by words without including punctuation. We also removed English stop words, that is, words that don't have real meaning. Finally, since we have long texts, we will remove words that appear in less than 10% and in more than 90% of the documents. Now we are ready for word embedding. Embeddings are a low-dimensional representation of high-dimensional data. They start with a single token, which in our case is a single word. They are based on pre-trained models for the selected language, which looks at a word and places it in its corresponding vector space. In other words, it embeds it. In this way, words that have similar meaning or come from the same family will be placed close together and will have a similar embedding vector. Once all the words are embedded, the procedure then averages all the word vectors to produce a single document vector. In practice, the procedure is simple. Connect document embedding to preprocessed text, and Orange will compute the result server-side. You can change the language of the model or the aggregation of word vectors. A quick look at the data table shows us we now have 300 additional numeric features that describe our documents. Let us now do a simple clustering with cosine distances and hierarchical clustering with word linkage. I will label the tales by their title. A quick glimpse into Dendrogram shows us that animal-themed tales are clustered together based on the type of animal they talk about. Document embedding is a great tool for describing documents with numbers. It is usually more accurate than bag of words, since synonyms are placed close together,
And as such, the model doesn't rely on words alone, but also on their meaning. Bag of words, on the other hand, is easier to interpret. The choice of the technique is up to you. Ever wondered who is leading the debate on social media? Who is that one person that everybody mentions and that keeps coming up on our feed? Today we will learn how to construct a network of mentions and find the most popular account in the bunch. We will use the Twitter widget to retrieve 500 tweets in English with the hashtag machine learning. This will output a subset of the debate on machine learning with all the hashtags, @mentions, text, and so on. A quick look in a corpus viewer gives us an idea of what the corpus is about. Great! Now we are ready for some pre-processing. Our aim is to retrieve only @mentions. First, I will remove everything I don't need, lowercase transform, and filtering, for example. Secondly, I will select the tweet tokenizer, since we're dealing with tweets. This will keep the @mentions as they are. Finally, I will add a regular expression in the filtering section, which will keep only words that start with @. The expression can be copy-pasted from the description below. Now, our data is ready for the final part. I will use Corpus to Network widget to compute the network of mentions. The widget outputs two things. One is a network of documents, where an edge is created between two documents if they share at least the number of words specified in the threshold parameter. The other is a network of words, where an edge is created if the two words appear in at least the amount of documents specified in that same parameter. The latter is what we will use in this case, as we wish to observe how words co-occur in our corpus. Also, we will set the window size to 100. This will create an edge between two words if they both appear within 100 words from each other. For tweets, this is sufficient to capture co-occurrence of @mentions in the same tweet. To observe this network, we will use the network add-on, which you can install in Options add-ons. I will connect Network Explorer to Corpus to Network. Besides sending in the constructed network, I will also add node data, which will give us interesting information about the nodes. In the Network Explorer, I will set the size of the node to word frequency. That is the number of times the word appears in the text. Finally, I will label the nodes with words. The network I get is interesting. Seems like there is a larger debate here with several people talking to each other. However, the most mentioned person does not get mentioned with the others. Today we have learned how to retain only mentions in pre-processing, how to construct a network of words from Twitter, and how to explore the constructed network. Stay tuned for more text mining videos. Social media are full of interesting data on human behavior, and sentiment is one such thing. Sentiment analysis gives us a quick glance into emotions in any kind of text, and can be used for brand monitoring, review analysis, observing story arcs, and for recommender systems. In this video, we'll learn how to extract sentiment from text with Orange. First, let us get the data. We will use Twitter widget to retrieve tweets with hashtag machine learning to see how people feel about this field. You can use any other keyword or even browse by @mention. We will keep the analysis manageable by retrieving only 100 tweets in the English language. Let's go! I always like to check my data in a corpus viewer. We seem to have some podcasts, articles, retweets, and so on. Now it's time to compute sentiment scores. Sentiment analysis can be lexicon-based, semi-supervised, or supervised. In Orange, we're using lexicon methods, which means we store lists of positive and negative words, then compute how many occurrences of each there are in the text. The approach we'll be using, Vader, is a little smarter and can work with phrases, negations, and punctuation. So 3 exclamation marks will count more than a single one. Also, it doesn't report just on a single score, but will report on a positive, negative, and neutral score, and on the final compound score. Okay, we have computed the scores for our corpus. The easy way would be to use data table, then find the scores, and sort by frequency. But this is just no fun. Let us plot them instead. I will use heat map, which shows all 4 attributes and where the blue represents the lower scores, and the yellow and the white, the higher scores. Still, our data is unorganized. Let us use clustering to put rows with similar scores together. Perfect. Now my negative scores are at one end and the positive ones at the other. Select, say, the negative cluster and observe the texts in the corpus viewer. It seems like some are indeed negative, but others not so much. Certain words, such as problem, are considered negative. Yet, in the language of machine learning, they're totally normal. We deal with problems every day. To finish on a positive note, let us select the positive cluster and inspect it. Just as before, we have some truly positive tweets and some that are ambiguous. Today we have learned how to extract sentiment from text in Orange, how to plot it in a heat map, and how to explore the results. Stay tuned for more text mining videos. Social media is not just for fun. It can also be useful for understanding people's behavior. Especially on Twitter, with an open access to its content, it's easy to follow and analyze topics, political opinions, friendship networks, trending hashtags, brand sentiment, and so on. In this video, we'll learn how to retrieve data from Twitter, how to preprocess it, and uncover interesting topics from the corpus. Twitter provides a way to retrieve tweets, but you will have to first register and get an API key. The link to the Twitter developer site is in the description below. Next, you will have to apply for a developer account and create an app. Once you have created an app, go to Keys and Tokens, then copy the key and secret key, and paste them into the Orange Twitter API dialog. Now the Twitter widget is all set up. Say we wish to see what is trending in the machine learning community. I will enter #machine-learning into the query box and set the language to English. I will go with just 100 tweets to keep things simple, but you can retrieve as many as you like. The best way to observe text data is with Corpus Viewer widget. Here I have all my tweets. For a concise view, I will select Content in Display Features to see only the content of the tweet. Then I will use Ctrl-A to select all the data. Perfect! Now I can read the tweets one by one. But of course we won't do that. If we had thousands rather than 100 tweets, it would be impossible. So instead, let us look at the most frequent words to see what a corpus is about. We will connect word cloud to Twitter widget and see what we got. Oh boy, lots of useless things. Our query and some punctuation. Let us remove this with preprocessing. We already have some presets here. We will keep the lowercase and add remove URLs. The word cloud had HTTPS ranked at the top. But this is not an actual word, so let us remove it. The preview in the bottom left shows the first few tokens, so I can see how my data is changing. The next step is setting the right tokenization. Instead of splitting by word, we will use a pre-trained tweet tokenizer, which is able to extract hashtags, mentions, and emojis. The downside of this tokenizer is that it also returns punctuation, which we will remove with filtering by regex. The preset regular expression will remove most punctuation characters. A quick glimpse into the word cloud shows us our data now makes much more sense. The top hashtags used with machine learning are AI, artificial intelligence, data science, and deep learning. Finally, let us uncover what these tweets are about. We will use topic modeling to uncover latent topics in the data. There are 3 methods for topic modeling. We will use latent dirichlet allocation, which is a generative method based on word co-occurrence. We are asking for 10 topics. In the widget, we see the defining words for each topic. An even nicer way of observing topics is in the heat map widget. Select clustering with optimal ordering to cluster topics by how frequently they occur. Wonderful! Now I can select a subset of documents with high topic frequency and observe them in a corpus viewer. Today we learned how to retrieve data from Twitter, how to reprocess it, how to extract interesting topics, and how to plot them.